This lecture is about proof terms for classical logic. But before we discuss proof terms for classical logic, we'd like to learn programming with continuations. Programming with continuations. So this is the prime example for motivating the development of continuations. This example is written in standard ML, which is similar to OCaml. So this function multiply takes a list of integers and then calculates the product of all the elements. So basically, we'd like to multiply all the elements in the given list L and calculate their product. So this is a simple implementation, recursive implementation. If the list is nil, we return 1, and otherwise, we make recursive call and then multiply the result with the first element in the given list. So this is a fine implementation of this recursive function multiply. And we'd like to optimize this multiply. So the first idea is, if we encounter 0 in the given list L, we can instantly return 0 because in the presence of a single instance of 0 in the given list, the whole product is 0. So this implementation, this revised function multiply prime, is based on this idea. Still, it's a recursive function, but compared with the previous implementation, now we have this case in the pair matching. So if the list is nil, then we return 1. Otherwise, we first check if the first element is 0, in which case we just return 0 without inspecting the remaining elements in the list L prime, the remaining elements. If the first element is not 0, we proceed normally. We make recursive call and then multiply the result with the first element. So it looks like this is a slight improvement over the previous recursive function, because if the list L happens to contain an instance of 0, we can take advantage of the second clause here, and then we don't have to inspect the remaining elements. However, if this L does not contain any instance of 0, then we are only wasting the computation where we compare every element with 0. So we take the second clause in the pattern matching, but this is always false. So we just wasted the computation of comparing all the elements with 0. But the real problem with this implementation is, even if the list L contains, say, 0, for example, L is 1, 2, 3, 4, and 0, and 5, 6, etc. So even if the list L contains an instance of 0, still we have to return to the previous call. So we have to perform returns for recursive calls. So if the list L contains an instance of 0, we will return just as many times as there are elements before the first instance of 0. So in this case, we will have to return 4 times. And we could say the cost of returning from recursive calls may not be negligible. So let's try to further optimize this recursive function in SML. In SML, we have some constructor called, a new constructor called callcc and throw. This is basically an ideal solution that uses a programming constructor called continuations. So informally, this callcc with this function declares a global label. Say we declare label return label, and this throw performs a non-local transfer to the previous label declared, the label declared previously. So what happens is, when we encounter this callcc with this function, we declare a return label, and then we proceed to evaluate the main function body. So now we are evaluating this function body. So we proceed normally until we hit this throw. So we have two arguments in this throw statement. The first is a label, where we will be transferring the control. So now we will be jumping back to this label. And we have another argument, 0, and this one will be the value that will take the position of the whole function body. So when we encounter this throw construct, what happens is we just cancel what is currently happening, and then just go back to this label, and then use this 0 as the result. So what these two constructs, callcc and throw, allow us to achieve is we can make non-local transfer by skipping all these function returns. Compared with the previous implementation here, when we encounter 0, we still have to return recursive calls as many times as there are elements before the first 0. But in this case, let's just say the list L is 1, 2, 3, 4, 0. So we make recursive calls 5 times. Now we hit the first 0. And what happens is we don't even return, because we are going to make a direct transfer of control to this label. So in some sense, we go back in time. We go back in time when this multiply double prime was called, and then proceed as if the function body was 0. So notice that in this case, if we encounter 0, we don't even return this recursive calls. So we save the cost. So that's the informal introduction to this new construct, callcc and throw. So basically, callcc declares a label, control label, and throw allowed us to move transfer the control to this label with an argument like a 0 here. So that's the idea behind the callcc and throw. Now let's consider the reduction rules for callcc and throw using evaluation context. So back in programming language course, we learned this beta reduction rule. And this beta reduction rule exploits this evaluation context. So for any given expression E, we can decompose this expression into a unique evaluation context kappa and next expression to be reduced with the beta reduction. So let's say this is E prime, and this E prime is beta reduced, because we are going to apply beta reduction to this expression E prime. So now we can reformulate the operation semantics with this single reduction rule in conjunction with the definition of evaluation context. So this definition of evaluation context specifies a unique reduction strategy, such as call by value or call by name, etc. And we only need this single reduction rule. So I'd like to we remind ourselves with this beta reduction rule. Now let's see how we can compute call CC and throw. In the case of call CC, the current evaluation context is kappa, and this is beta reduced. Now we have just encountered the call CC. What happens is we take the current evaluation context kappa and then use this current evaluation context kappa for this variable x. So basically, we capture the current evaluation context and carry it around in evaluating expression E or inside the expression E. Recall that this evaluation context kappa is equivalent to call stack. So every time you make function call, this call stack grows in size, and every time you return from function call, this call stack shrinks. And this evaluation context is basically call stack. So this call CC, when you are reducing call CC, you take the body of this call CC expression E and capture the current evaluation context and store it in variable x. And what about the throw? In the case of a throw, the current evaluation context is kappa, and we have this evaluation context kappa prime, which was captured in the previous call CC. And then what happens is we just ignore the current evaluation context kappa and restore the previous evaluation context kappa prime and fill the hole with a value v. So that's what happens when we reduce the throw. So let me show in this way. Suppose that we started the reduction of some expression, and after a while, we have this evaluation context and call CC x.e. And then in the next step, so this is beta reduction. So this is beta reduction, and we take this evaluation context kappa, and we evaluate the expression E, but every instance of a variable x inside E is basically replaced with this evaluation context kappa. So with this notation. And then we keep reducing the expression. And let's just say later, we have this kappa prime with throw value v to evaluation context kappa. So this one and this one are the same. So what happens here is we have different evaluation context kappa prime, but it doesn't matter because we are going to throw this value v to this evaluation context. So in the next step, we have kappa with value v. So effectively, we achieve a time travel. So when you encounter throw v to k, v to kappa, you go back in time and come back here. But instead of reducing expression E, you reduce value V. So you go back in time, and instead of reducing expression E, you just take the value V. So go back in time and use a different value. That's what you can do with the call CC and throw. Now, let's go back to the classical logic and how these two constructs, call CC and throw, related to classical logic. So in the previous lecture, we developed the natural deduction system for classical logic, where the idea was, instead of this hypothetical judgment where we use this context gamma, we introduce another context delta, and this gamma is a collection of true judgments, and delta is a collection of false judgments. And we have these two inference rules, in addition to all these rules inherited from constructive logic. So this control up rule and control down rule. So let's review these two rules. Suppose that you'd like to prove A true in classical logic. So we assume this classical logic. And in classical logic, the essence of classical reasoning is proof by contradiction. So you assume that A is false, and then you try to generate a contradiction. And perhaps the simplest way to generate contradiction is by proving A true itself. In the presence of this assumption A false, the proof of A true directly produces a contradiction because A false and A true contradict each other. And you'd like to read this rule upward in a bottom-up way. So this rule is called contra-up rule. And there is another rule which is best read in the top-down way. So this time we start with an assumption of A false and a proof of A true. So we have this classical logic. So if you read this rule top down, you have already generated the contradiction. So if you are given the same set of assumptions or hypotheses, you can produce anything because essentially you have just generated a contradiction, so you can prove anything. So this is a contra down rule because this rule is, perhaps you want to read this rule top down. So what is interesting about these two inference rules is both rules have the identical premise. The premise in both rules is identical. You have the same premise here and here, but the conclusion is different. Conclusion is different. So this is different because in the case of contra up rule, you want to read this rule upward, whereas in the case of contra down rule, you want to read this rule in a top down way. So in addition to all the inference rules from derived from constructive logic, so these are all derived from constructive logic by simply inserting this delta context. Now you have the full system of classical logic using natural deduction. Now, the next exercise is we'd like to introduce proof terms. Proof terms for this control up and control down. So here is the development. So this is the system of inference rules based on natural deduction in classical logic. So the hypothetical judgment has this form where gamma is basically a collection of truth judgment and data is collection of false judgment. And now we'd like to reformulate the system using proof terms. So with this typing judgment, gamma, delta with proof term M has a type C. And delta is just a collection of type bindings. So X has a type A, blah, 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 blah. And for delta, we use this notation. We'd like to use X has a type A false. So we are currently abusing the notation. Here, A false stands for A is false, it's judgment. But here, A false is a type. So it turns out that this type, A false, is basically a type of this evaluation context for type A. So this evaluation context is expecting an expression of type A. Or we could say just type of continuation of type A. So A false means the type for continuation of type A. So perhaps a better syntax for this one is A continuation, or put simply A cont. But in the course notes, we don't give the details of these operational semantics for continuations. So we'd like to reuse this A false as a type. So you can just read A false as some sort of a type instead of judgment here. Now let's introduce proof terms corresponding to core CC actually contra up and contra down. So we have contra up rule. It says gamma delta, I want to prove A true, then assume A false, and then produce contradiction by proving A true. So this is the classical logic. And let's reinterpret this inference rule using proof terms. So we have a gamma, delta, and some proof term of type A. And in order to build a proof term of type A, assume X has a type A false. Or if you are still confused, you can imagine that this A false stands for A continuation. And then you build a proof term of type A. But the question is, what is the proof term here? So again, we may choose any syntax for this proof term as far as it contains everything from the premise, in particular this proof term M and this continuation A false. And the syntax that we'd like to use is call cc. So we'd like to use call cc x has type A false, and we are going to evaluate proof term M. So call cc actually stands for call with current continuations. And we call this rule call cc rule. Next, let's translate this control down rule. Control down rule starts with the same premise, A false, kappa, A true. You have control down rule. And the conclusion is, with the same hypothesis, you can prove anything. So let's translate this rule using proof terms. So you have gamma, delta. This A false is now translated to X has a type A false, and you have some proof term M of type A. Now, with the same context, you have a proof term of type C. And again, you may use any syntax for this proof term, and we'd like to use this proof term throw M to X. And this rule is called the throw rule. So we are not going to develop the full operational semantics for call cc and throw, but it helps a lot to interpret this call cc in terms of evaluation context. So remember that when you have call cc xa.m, where the current evaluation context is a kappa, you basically you keep evaluating this proof term M, but X has been replaced with the current evaluation context kappa. So we are not going to be developing the full semantics, but that's the intuition, the basic idea behind this call cc. And in the case of a throw, let's say we have a kappa prime with the throw M2. This is the kappa, evaluation context kappa. And then we just disregard the current evaluation context and reinstantiate restore the previous evaluation context kappa with this value v, this value m. So this is how we interpret this call cc and throw in the context of evaluating terms. Now let's see an example. Previously we saw an example where something like a time travel occurs. So when you throw some value to evaluation context, you perform time travel back to the time when this call cc was encountered. And we can find a similar story in this example. So I would like to find a proof term for this law of excluded middle. So it is going to have type A, disjunction, negation A. So let's do this. So this law of excluded middle proof term is going to be first call CC with type A disjunction negation A. So here we are supposed to find a proof term of type A disjunction negation A. So we remember the current context, or we declare a label here so that we can come back to this label later at any time. Now, so this is going to be a proof term of type A disjunction negation A. So here you are supposed to find a proof term of A disjunction negation A. Now you have to make a choice, taking the left side or the right side. So we don't know which is the correct choice at the moment. So we decided to take this branch. So therefore, it's going to be injection right with the left side of type A. Now you have to find a proof term of type negation A here. So this one has a type A disjunction negation A. Because we have chosen this injection right, this proof term, whatever it is, should have type negation A. So it's going to be lambda y A and another proof term of type bottom, because negation A is basically A implies bottom. Now you are supposed to find a proof term of type bottom. At this time, we realized that the previous choice of injection right, that is, the previous decision to take this right branch is wrong. So we'd like to go back in time and then correct the wrong decision. So what we do is we throw this value y of type A to previous context x. So notice that when we reach this point, we have a value y of type A. So now I'd like to change my mind. Originally, when we are at this stage, we decided to take the right branch. We decided to find a value of type negation A. So we proceed. But later, we find ourselves looking at a value of a type A. So we realize that we made the wrong decision here. So we go back in time with this value y of type A. But I made a small mistake here. So before we go back in time, we have to build a value of A disjunction negation A. So returning this value y without any further modification would be wrong. So we'd like to go back in time with a value of type A disjunction negation A. So what's going to happen is here we are going to throw a value of type A disjunction negation A to x. Because we have a value of type A, we can now construct a value of type A disjunction negation A using injection left y with the annotation negation A. And then we pass this injection left y to this context x. So the story goes like this. you are supposed to find a value of a type A disjunction negation A. So first, you remember the current execution point by creating this label. You can think of X as a label created at this moment. Later, you can always go back to make control. You can transfer the control back to this label X. So that's what we do first. And next, you have to create a value of type A disjunction negation A, but you don't know which side would be the right choice. So you take the right choice. So you are going to create A disjunction negation A with the injection right. Now you have to build a value of type negation A here. So you create this lambda, and then you have to find a value of type bottom. And this time, you realize that our ultimate goal is to create the value of A disjunction negation A. Now you have a value Y of type A at hand. So now it's pretty easy to create A disjunction negation A by taking this left side. So injection left Y gives us this value of type A disjunction negation A. But this contradicts our previous decision. The previous decision was to take this right side, but here we take the left side. But that's fine because we can make this time travel. So we go back in time where X was created and then pass this injection left to Y. So basically, we come back in time, but at this moment we have injection left to Y, which has value of which has type A disjunction negation A. So whichever is the case, we always end up with an expression of a proof term of type A disjunction negation A. So which completes our journey.